Okay, chapter 10, problem number 18. The problem reads this. Water and then oil, which do not mix, are poured into a U-shaped tube, open at both ends. They come to equilibrium as shown in this figure. What is the density of the oil? And we're given the hint that the pressures at points A and B, which are at the same height, are equal, and we're asked why. So we have this basic idea that the pressure at 2 points within a uniform fluid, as long as they're at the same height, they should be at the same pressure, and basically that is Pascal's principle. Okay. So what we should do is go ahead and use that fact, write the hint that PA is equal to PB, and we're going to use this equation in order to somehow figure out what the unknown density of this oil is. Okay, so at least conceptually, this is our picture. So concepts. The types of things that we've talked about in this unit are so things relating to fluids, which would be density and pressure. So we want to keep in mind what their definitions are. But I think probably most important is going to be how does pressure vary with depth? Since we're given this hint that the pressures at points A and B are the same, presumably we can figure out how their pressures are related to the atmospheric pressure, which is sort of on the outside. We can figure out what the equation is that tells you what the pressure at A is, what the pressure at B is, set them equal, and that'll be hopefully enough. So pressure variation with depth. Okay. So again, density, Greek letter rho, pressure, capital P, and pressure variation with depth. That is an equation that looks like this. The pressure at some depth is given by some initial pressure, which is oftentimes the atmospheric pressure, but not necessarily. It's whatever the starting pressure is at the top of some fluid. And then if you go down a distance h, then the pressure goes up by an amount given by the density of that fluid, gravitational constant, and the depth that you go, h. Okay, so this will hopefully be enough. Let's see if we can figure out what the pressure is at points A and B. So keeping in mind that this setup is given with there's some background pressure, which we can call P naught, the atmospheric pressure, which is sort of living everywhere. And this pressure doesn't vary that much in the atmosphere. We can actually compute this, and hopefully we've done this in class. If you ask how much does the pressure vary from the top of of this U over here to the top of the fluid over here, that amount of pressure change is very little because the density of air is very low. So the pressure at this surface and this surface is basically the same. It's atmospheric pressure. When we go to figure out what's the pressure at A, apparently it's given by the atmospheric pressure starting, and then it goes up by an amount given by the density of the oil, G, and this drop in height, the 27.2 centimeters. So let's go ahead and do that. So I'm going to write this as rho of oil, G, and then I'm just going to call this H1. We know this is the number, but it's sort of better to do things with algebra and then plug in the numbers later on. That's pressure A. Pressure B, it's the same idea. The starting pressure is basically the same, atmospheric pressure, and then it goes up by some amount given by the depth from the surface of the fluid here to point B. So we need that distance here. Okay, what's the fluid involved? That fluid is water, G, and then some new depth H2. That is this distance here. And hopefully at this point in the semester you realize the benefit of drawing a picture. You realize that this depth is not 8.62. In fact, it's this full depth, 27.2 centimeters, minus the 8.62. That's what H2 should be. We'll plug in those numbers in a moment. And I realize now that I've written this as lowercase a, which means that perhaps it would be better to do that over here to not confuse everybody terribly. Let's set these two things equal. You'll notice immediately when you do that, I'll go ahead and write everything out, that the initial pressure of the atmosphere actually doesn't matter at all. This is setting PA equal to PB. Clearly you can subtract the initial pressure. And once you've done that, you realize you have this term equal to this term. Apparently you can divide both sides by g as well. I'm just going to do that in one step. Cross out the g's. And ultimately what we want is the density of the oil. We have density of oil times H1 equal to density of water times H2. Apparently that means that the density of the oil is equal to the density of the water times the ratio of H2 over H1. Okay, and now we can simply plug in some numbers. The density of water, 1.000 times 10 to the 3 kilograms per meter cubed. That's the sort of the standard number that we're going to use for water unless we're told otherwise, like it's seawater, for example, is salty and has a slightly higher density. H2, that's this number here. That's going to be the 27.2 centimeters minus 8.62 centimeters. Why don't we go ahead and do that in units of meters, because ultimately we want something that has units of kilograms or meters or seconds or something like that. So 0.272 meters, that's this full height H1, minus 8.62 centimeters, which is 0.0862 meters. Okay, that should be our H2. Check that that's true. And divide that by H1, which is 0.072 meters. Okay, what you find is this comes out to be, depending on how you write it, 0.683 times 10 to the 3 kilograms per meters cubed, or if you like, you can write that as 683 times 10 to the 0. In other words, 683 kilograms per meter cubed, and then we just stop and do a sanity check. How does this compare with water? Well, water is, 1,000 kilograms per meter cubed. This is 683. It has a lower density. Does that make sense? I think so. In order for this water level, or this liquid level to be higher than this liquid level, if you like, basically the amount of mass sitting above point A has to be equal to the amount of mass sitting above point B, and the only way you can have a larger volume of fluid is if the density is lower, so that this mass here is equal to this mass there. So it makes sense.